All right, in section 2.1, we're going to start looking at our concept of a limit. So what is a limit? So a limit, we'll define it as a real number that f of x approaches from both sides as x approaches c from both sides. So as our x values approach a given c value from both sides, we're looking for a real number that our f of x values will approach from both sides as well. This is what we call a limit. We generally write a limit like this, LIM, limit, as x approaches c. So the x values approach c from both sides of some function that is going to equal our limit L. So we're going to look at lots of ways to calculate these. We're going to first start looking at them numerically, kind of using tables and things like that. We'll then transition to looking at them as a graph, looking at a graph of a function. And then in future sections, we'll actually look at them analytically or using algebra and some different techniques to actually find these limits. Limits are really important. They are really the foundation of a lot of calculus operations. Some of the major things we will use will be based on limits. So if we look at doing this graphically, I want to find the limit as x approaches 1 of negative 3x plus 5. So what I'm going to do here is I've picked some x values that are right around 1. So here's the limit value that we're looking for. So what I'm trying to do is try and find some numbers that are smaller than that and some numbers that are bigger than that, because these two rows will approach that x value of 1. So the x values are getting closer to 1. I went 0.9, 0.99, 0.999. So those are getting smaller and smaller and smaller than 1. And then 1.001, 1.01. Really, I'm going to read them kind of going from the ends to the middle, because that's how x is approaching. This top is showing x is approaching 1 from both sides. So then if I plug those numbers in, if I plug 0.9 into the function, I'm going to get 2.3. If I plug 0.99, I'm going to get 2.03. And if I plug 0.999, I'm going to get 2.003. Now I could plug in 1, but I really don't care about what happens at the value. This really doesn't concern me. Really, it's what happens as you approach from both sides. Now this value is 2, but I really don't care what it is, because it's really what's happening as I approach it. 1.001, if I plug that in, I get 1.997. If I plug in 1.01, I get 1.97. If I plug in 1.1, I get 1.7. Again, just plug it into that function. And 1.25 will give me 1.25. So as I go from the left and the right to the center of the x, if I do the same for the f of x or the y values, so if we look at this, these seem to, of course, approach 2. So these are getting closer to 2 by decreasing. These are getting closer to 2 by increasing. So I would say the limit is 2. So the limit as x approaches 1 of negative 3x plus 5 is simply 2. Now there'll be other ways to check this in the future, but this is a pretty nice way. The biggest thing to remember about limits is it doesn't matter what happens at the point of the limit. It's what happens as you approach it. Okay, let's look at this next one. So if I take this function and start plugging all the same values in, now I do want to mention that I'm only plugging the same values in because we're approaching 1 again. So anytime you're approaching 1, you can do the same thing. If this were 2, x approaching 2, you might do 2 and 2.001 and 1.999, just depends. But again, in this case, this top, both of these sides is the x approaching 1. So we want to see what the y is approaching. So I'm just going to plug these numbers in. So I get 1.9, 1.99, 1.999. At 1, I actually get undefined, because 1 minus 1 in the denominator is 0. You can't have a 0 in the bottom. 2.001, 2.01, 2.1, and 2.25. So now if I look what happens to the f of x values, what happens to the y values as it approaches that. Well, this one we're up to like 1.99 and this one we're at like 2.01. So I feel fairly confident saying the limit is 2. Now in this case, there was no value like above. This was actually undefined. But again, it doesn't matter what happens at that point, only what happens as you approach it. So let's go look at our next example, which is the limit of e to the x over 1 over x minus 1 as x approaches 1. So same x values. So again, these top ones are saying from both sides, x approaches 1 from both sides. And so if I plug these in, I get negative 14.6. I get negative 169.1. I get negative 1715.6. At 1, I get undefined. At 1.01, I get 1721.0. 174.6, 20.0, and 9.96. And I have rounded most of these values. So now, if I look from this side, coming from this side, you can see these are getting to be bigger and bigger negatives. But from this side, these seem to be getting bigger and bigger positives. So if one side is getting to be bigger negatives and one side is getting to be bigger positives, they're not approaching the same number. They have to be approaching the same number for it to have a limit. So in this case, I'd say the limit does not exist. There is no limit because the f of x or y values don't approach the same number. Those are not even close to the same number. And you could get even closer. You could do more 9s and 1.00001, and it'll just get further and further apart. All right, let's look at our next one, which is the limit as x approaches 1 of the natural log of x over x. So again, nice thing, it's the same x value, so I don't have to worry about those. So really, I'm just looking at my y values. So the y values I get for 0.9 is going to be negative 0.117. And then I'm going to get negative 0.01. Then I'm going to get negative 0.001. At 1, it's actually 0. At 1.001, we get 9.98 times 10 to the negative 4th. And then 0.009. And then 0.086, and then 0.17. Now, I did this one because it has the scientific notation with the times 10 to the negative 4th. This essentially, remember, is like 0.000998. You're basically moving the decimal point 4 places to the left. So as x approaches 1 on both sides there, does the f of x or the y values appear to approach something? And I'd say it's pretty clear that they're getting very, very small. They're getting very, very close to 0. So this would have a limit of 0. So that's kind of the numerical way we'll find limits. We can also find them using a graph and then in the future with algebra. So let's go ahead and look at a graph example, how we can find it with a graph. Now remember, the limit is going to be what values does f of x approach the limit as x approaches c. That's the limit. So in this graph, you'll see we have this kind of graph. It keeps going on up and up and up. Here we get to a gap in the graph, so it is an open circle. So the point on the graph is down here. And then it kind of continues up on this pattern, goes down here, and then kind of arcs up here, and we'll say it just kind of keeps going. So this is what our graph looks like. So we have that one kind of missing point in the graph. So we're going to use this graph to find a couple limits. So the first one says, what is the limit of this graph as x approaches 7? So now a graph is not a perfect tool because, you know, we can't really pick out the exact values sometimes for the graph. So here's 7. So if I look at the graph, so here is kind of 7 on the graph. So as these y values, so these y values are approaching this way from this side, And as the x values get closer from this side, the y values get closer to that. So if we look at it, does that seem to get close to any value? If I had to guess, I would say this gets close to pretty close to -2. That is going to be the y value that the graph approaches from both sides as x approaches 7. Now what about -10? The next limit says the limit as x approaches -10. That's over here. Well, the same thing, the y values just to the right of it are approaching this way, and the y values from the left that are smaller are approaching this way, and they're basically pointing toward the same number. And that number, if I take it over, appears to be +2. So the graph approaches those values because they're just the y values. The next one is 4. So let's jump over to 4, which is right here. So the y values as we go on this side, and the y values as we go on this side of 4, which is right here. If I take that over, I appear that, well, we'll say that's about 6.5. 6.5, somewhere between 6 and 7. And again, it is not perfect, for sure, but it's just kind of an idea. Now the most interesting one is the last one, which is what happens as it approaches -6. Now -6 is right here, and this is the interesting part of the graph because we have this open circle here, and it drops down here. So if I said what's f of -6, it is 2 because the solid dot is there. But the limit is not 2 because the limit is what happens as you get close to that point on both sides, not what happens as you get to that side. So if I look at these two red arrows as I'm coming from values smaller than that and larger than that, it does not approach 2. It actually approaches this empty circle up here of 8. So the limit is actually 8 of this one because the limit is where the graph approaches at that point, not what happens at that point yet. Now sometimes limits will not exist. And typically the way they will not exist is if they don't approach the same number. So if a function approaches different numbers from each side, or no number at all, we say the limit does not exist. So what would it look like if the limit does not exist? So we have a couple examples here. So this first one is some kind of function where the graph is kind of going off to infinity this way and going off to infinity this way. But there's no real number this approaches. Remember, the limit has, and this is the limit as we go to 0. So at 0, it's not approaching a real number. It has to approach a real number. Now, there is such a thing as an infinite limit, but right now it has to approach a real number, and this doesn't really approach an actual number. So we say the limit does not exist, or just DNE. Another kind of way a limit doesn't exist is if you have a jump. So something like this would be a jump. So as the limit, we're looking here at the limit as x approaches 2, because that's the interesting point here. So as I go this direction, the graph seems to be appearing to go to 1, but if I go to this direction, it appears to be going to 3, and then the actual graph is at 2. Not that that matters, it's really what happens as you approach it. But since they're approaching different numbers from each side, the limit does not exist. So some things we want to look for limits that don't exist. So one thing I'd like to look for is I'd like to look for things at infinity. So anything that's kind of taking off to infinity or down to infinity, things like that, that's typically a non-existent limit. Anything that has a jump. Anything that has a jump where it's going from one thing and then it jumps way up to another thing like in the previous example. Or any kind of graph that bounces or oscillates is an issue. something like sine, or not sine, let's do something else. So if I have something that looks like this, it just keeps bouncing back and forth and 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 back and forth. Sometimes that can be difficult to find. So anything that oscillates really, really quickly and you can't tell where the oscillation is at any given moment is a problem for limits. Now, we'll also see ways that we can do this algebraically, see the algebraic way that limits don't exist later on. All right, let's just look at a couple mixed examples. So I want to find the following limits, and I want to use both the graphical and numerical approach. So this says I want to do the limit as n approaches -5 of n squared plus 25. So what I did here is I went ahead and I put this in Desmos, and I went ahead and made a table of values around -5. So if you look at these are all numbers around -5. Some are slightly bigger, some are slightly smaller. But I want to see if this seems to have a limit. So as I go from this side to this side, I'm doing the x approaching -5. So I want to see, does the y values, do the f of x values seem to approach a number? So on the bottom, I see -0.100, -0.1, and the top I see -0.099. So in an actual point, I see -0.1, and that kind of seems that those are tending to the same number. So I would tend to believe this is going to 0.1, -0.1. And the graph, if I kind of look at it, this graph going this way and this graph going this way around -5, I think -0.1 is a good estimate. No, I'm not 100% sure, but I'm pretty confident looking at this table that's what it is. Again, we're not going to be 100% confident until we can actually do these algebraically. Okay, this next one, let's look at the limit as x approaches 3 of x plus 13. Now, this limit would have some non-existent parts for sure, like over here where there's no graph. That would be obviously an issue. But we're looking over at 3. So I'm going to use the graph first. So if I use 3 is right here. So as I approach from this side and I approach from this side, I would kind of just estimate it to be 4. And if I look at my table, I was approaching 3. So as I look at 3 from both sides, it appears that both sides of these are also approaching 4. So again, no reason I have not to just assume the limit is 4. If you start looking at these functions, it's not very hard to see how you can get 4 algebraically, so I'll let you take a look at that. See, with the 3 and the function I'm getting, how could you get 4? All right, the final one here I have is a piecewise function. So I have the limit as x approaches 0 of x squared when x is less than 0, 1 when x equals 0, and x when x is greater than 0. Now, in general, x squared is a pretty nice function, and x is a pretty nice function. 1 is just 1. The real question is going to be at 0, because this is where this graph breaks. Now you can see I've made a sketch of it here. So this is essentially x squared when x is less than 0. So if I wanted to show how I would do it by hand, I would just pick some values that are less than 0. And I'm going to pick 0 too, but remember 0 will be open. So 0 squared is 0, -1 squared is 1, -2 squared is 4. So those are some of the points you see on this parabola. The 0, 0, the -1, 1. So this is -1 and 1. So there's a point. And -2, 4. And you can kind of see there's that parabola. At 0, it's 1. So you see this solid dot here. And then for greater than 1, it's just x itself. So 0, 1, 2, because those are bigger than 0, and 0 will be open. So I just get 0, 1, 2, because I'm just plugging them into x. And so there's some of my points. There's 1, 1, there's 2, 2, and you can kind of see it going off in this direction. Now the question is, what is the limit as x approaches 0? And I can actually see these through my tables, because if you notice, this is the same point, and that's really important. Now this dot isn't, but it doesn't matter what happens at the point. In a piecewise function, at the points that are broken, we want to see the same y value. So as I see the graph as it approaches 0 from both spots, because it's going to that same number, there's no reason to think that this should not be 0. So I would say the limit of this one is going to be 0. Now, of course, the big thing is being able to come up with this graph of a piecewise function and being able to look at it. But when we look at it algebraically, we'll definitely look at some of these points where the graph is possibly broken for a jump and just see what happens at that point. All right, so if you have any questions, let me know on this first section of limits.